Now, to apply what we know here, we start out by doing something that doesn't seem at all related to any of this. And in fact, it isn't all that related. Okay? All we're really going to analyze here, and all we really got to in class, we never got to these functions. We'll do that next time. But we just got to the implications of F net equals negative kx. Okay, the first question that was posed on your document is, what's the potential energy at position x relative to the equilibrium position? Okay, now we had to get into a discussion, and it was appropriate to do so, of what do we mean by the equilibrium position. We got a mass suspended from a rubber band. Equilibrium position is where the mass doesn't move if we release it. Okay, the net force at this point is 0, meaning that the rubber band force is equal and opposite to the gravitational force. If the object goes below the equilibrium position, then we have more elastic force from the rubber band than we have gravitational force. Gravitational force doesn't change. So if we go down below the equilibrium position, we have more force from the elastic and the same force from gravitation as we did at equilibrium, which means we're going to have a net force upward. If we come up above the equilibrium position, there's less force. The rubber band is less stretched. You got less force. You still have the same gravitational force. Well, the two forces were in balance here. Now you're up here, and this force is less than it was, means you have a net downward force. So that means wherever you move, if you move away from equilibrium, you have a force back toward equilibrium. Okay, that's the negative sign. You take a negative k, multiply it by your position relative to equilibrium, and you get the force, and that force points back to equilibrium. Another thing you have to understand is that, as stated in the problem, we assume, and it's not true for rubber bands, but we assume, at least as a first approximation, that the force exerted by the rubber band is conservative. Okay, well, we also know that the gravitational force is conservative, which means that if all other forces are neglected, and there is really no other force that makes a significant impact on this motion over at least a short term, air resistance will eventually wear things out. We're ignoring the fact that the rubber band does lose energy. We're pretending it's conservative, so it's not going to lose energy. So if you ignore air resistance, this thing will keep going forever because there's all the forces acting on it are conservative. And we'll talk a little bit more about that. But the main point is that the net force is conservative because the net force then consists of the conservative gravitational force and the conservative elastic force, the conservative force exerted by the rubber band. If you reference everything to the equilibrium position, then gravitation being the same at every position, you never have to think anymore about gravitation. You just have to think about how the rubber band force, the force of the rubber band changes as you move above and below equilibrium. And the sum of the two forces will still be of the form F net equals negative kx. Now, we asked the question, and the question was posed. I mean, I didn't just throw you out into the water and let you sink or swim. I posed the question, what's your potential energy relative to the equilibrium position? Okay? And then I asked for definition of change in potential energy. Because the potential energy relative to equilibrium is the change in potential energy starting from equilibrium to wherever, to position x, let's say. Okay? So, nobody could give me a definition of change in potential energy. This is only about the 50th time I've said in class, you need to know this definition. Otherwise, it looks different every time you see it and you never connect anything. Nobody knew the definition, although some people given a couple of hints, were able to give me parts of it. You need to know the 11 words of that definition. Change in potential energy is equal to and opposite to the work done on the system by the conservative force. Now that's more than 11 words. It's more like 16 or 17. It's not beyond our capability to know those 16 or 17 words so that we can apply them whenever we need them. Rather than relying on this formula for potential energy and that formula and a formula over here and getting them all mixed up, we have one definition: equal and opposite to the work done by the conservative force. So, from the work done by the conservative force on the system, as we go from equilibrium to whatever, to position x, is just the integral from 0 to x of that force, negative k x hat dx hat. And I just use an x hat here because I didn't want to have an x here and an x here. This x is our variable of integration. This x is the position at which we want to get our potential energy. We don't want to have the same symbol having two different meanings. So our variable of integration, we put a hat on it. And the variable of integration doesn't even appear in our final result for the potential energy, for the change in potential energy. So we call it a dummy variable. It's something we put in here so we can use it, but it disappears before we get our final result. That's kind of a definition of a dummy variable. That's a standard term that's used throughout mathematics. Okay, now I have a note here that talks about what I said. Negative kx is sum of your gravitational and elastic forces. Both these forces are conservative, so negative kx is conservative. And then I recommend that you draw free body diagrams at equilibrium on both sides of equilibrium so you can understand what I said with my hands about how the net force if you go above equilibrium is down and the net force if you go below equilibrium is up. You should have free body diagrams. You should be able to draw free body diagrams that clearly show why that is and why the net force would have form negative kx, where k, as we saw last time, is the slope of your force versus length diagram for the rubber band.